Just
No
erase
5.
the 0 and the 5.
Oh, no. No, also this is a...
1.
No, sorry. 1,
3.
no, this is the second moment. That's the third moment. It's called the skewness.
Right.
This is the fourth moment. It's called the kurtosis. Yeah, suddenly a second moment. Of course, it's normalized by definition. It's 1. So this is, by the way, important for statistics. It's called the kurtosis. And if there's a fancy name, I forgot, about a camel. You know, in statistics, if it's above 3, it's called one thing, leptomonic, and if it's below 3, it's called something else. I forgot. Some fancy names to characterize. But anyway, if it's the limit of moment is this, it's asymptotically normal. So that's how to. So let's now go back to the side of the Durfee square. Let's go back to our beautiful proof of Sylvester and Durfee. And we get a more complicated combinatorial generating function. So now we want to find a formula for the random variable size of the Durfee square. So reminding you, the generating function for all partitions is this, and the beautiful argument of Sylvester and Durfee that I sketched before. Okay. And this is my definition of a theorem. Sigma P of n Q to the n. But we are interested in a more refined thing. We are interested in the double generating function. Not just the total number of citations you had, but also your eighth index. So we want a more refined thing. Let's call it P, okay, maybe H of nk. That's the total number of partitions of n that have Durfee square k. So it's a double generating function. And n goes from 0 to infinity, and of course k goes from 1 to square root of n. Put that in. A slight modification gives you this. Obviously, because if you want to give whenever the Durfee square a size k, I want to give it weight to the power k. So extracting the coefficient of q to the power n from this gives you, before, you only give you the number of partitions. But extracting the coefficient of q to the power n gives you the combinatorial generating function of the Durfee. So let's call it an H for Hirsch. So this is the generating function. So all you have to do, you look at this famous Euler-Lagrange formula and stick to the power k here, and all and behold, you get the generating function from these polynomials, the Hirsch or Durfee polynomials. And that's what what Canfield and Savage and Corteel studied without knowing how important it is for citation. So they studied very, very hard using this delicate analysis, very, very complicated. And I confess, I don't understand. I didn't try to understand. But nowadays we have computer. You go to Maple and you do simply add ADD q to the power k squared times q to the power k divided by mul for multiplication. 1 minus q to the power I goes from 1 to k, quantity square. And then you do Taylor. And you want the first, easily the first tensor coefficient, if you don't mind waiting maybe an hour. 1,000 is a second, but 10,000 takes a little bit longer. But still. And then you take the coefficients, you do coef, qi, and you have the sequence, not for Sloan, and well, it could be because the sequence of polynomials. So you have the sequence of the first 10,000 Hirsch polynomials. And then you go to this very short Maple program that I described before. And first, normalize it and make a probability generating function. You divide by P of n. And maybe you can do it in a second. So you have the probability generating function. Before it was the commutator generating function. So I have this. Now for the average, you simply take the derivative. And plug in t equals 1 and look at the sequence. And you can't help noticing that asymptotically is proportional to a square root of n, which is also true heuristically very easily. And then you see this square root of n. You have the leading term, c, and then you guess these answers. Okay, c0, c1, c2 of n squared. And you do least square. You try to fit this data, the 10,000 things, to get the closest coefficient of c1, c2, c3. And lo and behold, you get floating point. Very, very good floating points approximation for this. That coincides. And you can even guess the value of constant d. What was square root of 6?
I think it's on the board in the middle.
Oh.
No, it's gone.
Okay, square root of 6. I remember it. Log 2 over pi. Maple has a neat program called identify. And it works in some versions of Maple better than others. I think in earlier versions it works better than later ones because somebody maybe complained that sometimes it did the wrong thing, so now it's more conservative, and so it's much harder to get it. But when you did identify, I reproduced empirically this thing. So it would have been only conjecture, and this would be only conjecture, but the actual estimate, it was very, very reliable. And ditto for the variance. You do the same thing, the least square thing for the here, for the variance, and you get what I called it before. Very, very good approximations. And it fits beautifully, completely.
Did I identify work on the variance? Did they get that complicated expression you didn't?
I'm not sure if in the paper they have explicit things in terms of pi and e, or just maybe that's solution of the equation.
Okay.
I don't know how explicit it is. And frankly, I don't really care. But sure, you can look it up. It's cited in my paper. So yeah, professor. So, but now what about asymptotic normality? So we already know empirically or rigorously that the variance is proportional to the average. So you have concentration of the mean because standard deviation is the square root of the variance. So that's like the normal distribution, like the dot crossing, you are very, very close. But is it asymptotically normal? So doing the same thing as here, finding the standardized moments, the so-called alpha coefficients. Empirically, for the first 10,000 cases, remind you, f(k) over to the power k over 2. This empirically tends to a constant. If you just take the sequence of the limits, you get pretty close to 1, 0, 3, 0, 5. You get maybe 2.9, 4.99, but not terrific.
Should that really be 5?
No, 15. Stupid me. Thank you. Thank you. It's 3 times 5. 3 times 5 is 7. 3 times 5 times 7.
945.
Yeah, sorry. Thank you. Yeah, that's it. Yeah, I messed up. It's 1, 0, 3, 0, 15, 0, 105, 0. That's the moments of the Gaussian or normal distribution. But once again, you do this curve. So you do C0. Now you know the leading is at the constant. And you do asymptotic expansion. You guess an answer like this. And you want as many as you want. You can do up to maybe a little minus 5. And then you fit the last from 9,000 to 10,000 or even a few of them. And it's amazingly, now you get 3.000000001 agreement to 10 decimal digits. And also here, 15.00001. In my website, that's posted in the paper, so everything, all the data is there. In fact, it's in the body of the paper. You're welcome to download it. Yeah. No, sorry. For this, it's not. It's 3.0000000000000 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So probably after this it's a 1. I only went as far as the zeros. Then after 10 zeros it became a 1. But everything up to 10 decimal digits. And for me, this is proof enough that it's asymptotically normal. And this corroborates that indeed the H index was not that necessary, and then Alexander Young found out that indeed most people fall in the confidence interval. So you can predict the H index only knowing the total number of citations. So you don't really need anything fancy. But then again, it's a nicer number because it's not as big. If I brag, my number of citations is, in fact, in my case, let me brag. According to Google Scholar, the number of citations, if all my paper, is 5,441. I'm sure for nearly this much more than other people. And the H index is 33. So according to this, it should have been 39, the average. So my H index is a little bit less than expected, but still in the confidence interval of the 1%. I think not in the 5%, but in the 1% confidence interval, but barely. So it's an open problem why my H index is lower than it should be from the average. Whether it means good, something good, or bad about my scholarly activity, I don't know, hopefully it's something good. And anyway, it's good to be. So I'm still in the confidence interval, but in the low, in the low side. So, but you should take the H index with a grain of salt. Otherwise, and Grisa Perlman have a much lesser H index than me. Doesn't mean that I'm better than them. And in fact, for the case of Grisa Perlman, if you look at the database Messi-Net, stupidly, the thing that got him the Poincare conjecture and the $1 million prize, it's not even listed there because I'm sure it's referenced a lot, but it's only a preprint in the archive. He never bothered to submit it. So in the case of Perlman, it's not very accurate. So he has a low one. So with this one, probably he has the largest one is very, very, very big. But there's lots of open problems that still that people need to do. What about the largest? I think the most fair assessment of the scholarly quality is that the largest number of citations, not the H index. And so really, the H index is more a sign of how mediocre you are. I mean, you're productive, but mediocre. If you have an H index, you mean you have a lot of papers, and they're well regarded, but in my humble opinion, somebody who only has one paper with 10,000 citations has impact in science much more than somebody who has 100 papers, each of them was cited 100 times. So in a way, the H index is more mediocre. But it's interesting, and that's an open problem, and as far as I'm concerned, don't bother to do it the hard way, like Canfield et al. Do it my way, and it's open. In fact, a master student, Halu, is working on it. Look at the statistics. The largest part, citation, and 1. And the H index. And see if they are joint distribution. Maybe they are independently normal, maybe they are not. Find the asymptotic correlation, and then you have N1 and N2, and so there's a lot of stuff. Also, why stick to squares? You can take, and they pursued, used it to give a beautiful proof of the orthonormal identities. You can look at the sequence of rectangles. So K by 2K. So maybe that's a better index for equality. Look at the larger side of K that fits in the Venn diagram of the form K by 2K or K by 3K. And there are lots of variations, and then maybe you can compare these two indexes and have the joint distributions. And with this empirical approach, using symbolic computations, but in a very naive way, you can get non-rigorous, but very, very convincing results very fast. So there's lots of stuff to do. Thank you very much.